Okay, let me continue to introduce. Oh, excuse me. Okay. So this is the Dickey-Fuller test. Okay. So this means that, I'm sorry, this one. So if this is called non-stationary, and this is stationary. So we want to test, we like to have the result that it is stationary. Okay? So we like to reject the null hypothesis that this variable is, so this is by variables, either x variables or y variables, just variable itself. So Dickey-Fuller test, if we test the stationary of the variable, either it is x variables or y variables. You know, both of them we have to check whether they are stationary individually. Okay? All right? And what else I have to mention? Okay. Actually, the Dickey-Fuller test is pretty similar to the t-test, but it is different, a little bit different. So if we use the computer output, usually they will give you the result based on the Dickey-Fuller test, which is also similar t-distribution, but not really t-distribution. Okay, we will see that output later on. Okay, and this, so the Dickey-Fuller critical values depends on the version of the test. Okay, we'll say the version of the test later on, and the critical value will be different. And what that is different from if you check with the t-distribution. Okay, so do not check with the t-distribution, although it looks like a t-distribution. Okay, and really depends on the sample size and the version of the Dickey-Fuller test. So actually we have 3 versions of Dickey-Fuller test. Let's see. Okay, then first of all, this is just, this is already going to the co-integration. Okay, so let me put my own notes. Okay, continue my own notes. Okay, and also look at our textbook. Okay, there's 3 versions. 3 versions. What are they? Look at this one. This is okay. So this is what I say. We define delta y, right? So it expressed like 12.27, and beta 1 is like this one. So this is called stationary, and this is unit roots, so it's not non-stationary. And this is equivalent to test the null hypothesis gamma equal to 1, and the absolute of gamma is less than 1. Okay? And we say Dickey-Fuller test comes in 3 versions. So the first one is 12.27. What is 12.27 tell us in terms of regular regression? There's no intercept, right? Look at 12.27. It started with beta 1, yt minus 1. So there's no intercept. Did you see that? No intercept. Okay? And we say that most econometricians add a constant terms to the equation. So Dickey-Fuller test equation 12.27 becomes 28. So this one is with constant terms. Okay? And this is usually what we see from regression analysis. We usually have constant terms, what we call intercept. Okay? So this 28. And the other one is not only intercept, but also the time values. Okay? In case all the variables are inflated by times. You see the difference? There's 3 versions. So we can use 3 versions to check with the Dickey-Fuller test. And I think the next question you want to ask is, how do I know which one? How do I know which one? Usually, we can test 3 versions with all of them. Okay? All right? And I think most of the time, we will include intercept, and also, so most of the time we're using 29. Okay? Since time series data always involved with the time. So 1229 may eliminate all these factors which will identify the real situation or real relationship between X and Y. Okay? All right? So this is which of the equation should be used in practice. Then we have some guidelines. 27, if the time series fluctuate around a sample average of 0. This is just a guideline, okay? Since it fluctuates around the 0 means you don't have intercept. You don't need to have an intercept, right? Okay? The second one is 28. If time series fluctuate around the sample average, that is non-zero, because we do have some constant term over there. Okay? So that's 28. Then 29, if time series fluctuate around a linear trend, means there's something related to the time. Okay? Then we use 29 versions. Then in the literature model, 27 is called random walk model without drift. That means without constant. So without drift means no intercept. Model 28 is called random walk model with drift. Okay? And beta 0 being the drift parameters. And model 29 means called the random walk model with drift and deterministic trend. Okay? So-called because a deterministic trend value beta 2 is added for each time period. Means, take into the time trend as a factor. Okay? All right? So equation 29 is appropriate if YT is growing, and equation 28 is appropriate if Y is not growing. This is guideline, right? Okay, perhaps the best way to make this decision is to plot YT over time first, and then judge whether or not it appears to growing. Usually, GDP and consumptions are a good example of variable that are usually growing over time. GDP and consumption all related to the inflations, and they were growing, right? Okay, while most interest rate or unemployment rates are good example of the variable not growing. So one is using 28, the other one is using 29. Okay, anything else? Okay, this is saying that the standard T table does not apply to Dickey-Fuller test. Instead, the critical value are somewhat higher than those in standard tables, and that also depends on the version of Dickey-Fuller test. And most software package provide the critical value, so you don't have to find from some other table. Just look at output, okay? And I think this test is pretty, it's used a lot of time. It's been a lot of time, okay? So it's also popular in any kinds of packages, okay? So look at this one. Oh, okay. This is something we need to talk about, the ADF. Okay, this is called augmented Dickey-Fuller test. So let me introduce the augmented Dickey-Fuller test. If the error terms is serially correlated, okay? Since we are talking to the YT is equal to something and beta 0 or something, and no, we have the YT minus 1 something, right? So in this is what we call dynamic model. And the dynamic model, the terms of the error terms usually have zero correlation. Remember this one? This is a dynamic model. We use LM test to check with the zero correlations, right? Okay, so since this is related to the zero correlations, so if the error term is zero correlated, then the test must modify to take this zero correlation into account. And this adjustment is called augmented Dickey-Fuller test. And what we were going to use, EViews, usually is automatically using ADF, means augmented Dickey-Fuller test. Okay? And then whatever our terms, 12, 27, 28, and 29 become to this one. What's the difference? 27, again, no concept, but we have more these terms, right? We have this term. Did you see all these summations? Means the delta T black. Did you see that? So augmented Dickey-Fuller test is to increase these terms. Did you see that? Do we have that in our textbook? No. In our book, in our textbook, they don't say augmented Dickey-Fuller test, but actually, all this computer output is using Dickey-Fuller, augmented Dickey-Fuller test. I don't know how the Python does. So, Dickey-Fuller or augmented Dickey-Fuller. Yeah, usually is using augmented Dickey-Fuller test because the regression we want to test is most of the time is involved with zero correlations. So augmented Dickey-Fuller test is really consider the situations. Yes, Steve. Yeah, I'm using this. No. This I do the prime here. It's different from without prime. I mean the equation, and the difference is using the add one more terms. I like this. Oh, you mean the T? Did you mean this is? Oh, this one. Oh, okay. I'm sorry. Thank you. So this one, I should put the Okay? Huh? What happened? Oh, nothing happened. Just add this. I should add this one. Okay. All right. So the difference, 27 prime, 28 prime, 29. The difference with the original 27 to 29 is add this one only. Okay? All right? You don't have to worry about so complicated equation. If you see the output, the computer output, you'll be glad to see the computer output instead of just looking at all these mathematical equations which, really blow your head. But not engineering students, but, our business students where math is not good. Okay, all right? So maybe you're so bored since they're so easy. This equation is so easy for all of you, but it's hard for our business students. So I need to explain, take some more time to explain to my business students, okay? All right, and while ADF, this is just augmented Dickey-Fuller test, is the most used version of Dickey-Fuller test, choosing how many legs of delta y means this one with terms, okay? Values to include can be quite complicated. So the lag length is really, most of the try and errors, right? Most of the time doing the try and errors. Okay, that's the more, confusing parts in time series data. Okay, and okay, let's see the examples. What example here? Okay, this is an example. We're going to check the Dickey-Fuller test. Okay, and the y variable is y. Okay, there's three. If you don't remember, let's go back to chapter 9. Okay, we used this example in chapter 9. Let's see. Okay, chapter 9. 9 point, when we use the Durbin-Watson statistics to check the serial correlation. Okay, and again, y variable. Okay, y variable is per capita chicken consumption, which is y. Okay, in year T, in pounds in year T. And PC is the price of chicken in cents per pounds in year T. And PB is the price of beef, so the substitution effect. Okay? And in year T, YD is per capita disposal income. Okay, so we have 1 Y variables and 3 X variables. Let's check each one of them. Okay, with the ADF to check the stationary or not. Since, when we're talking about chapter 9, I'm using Y, then BP, BC, and the YD as a variables. In regular regressions, we have to assume every variables is stationary. But by chapter 9, we didn't talk about that yet. We didn't talk about those stationary or non-stationary yet. So at that time, we all assume they are stationary. But if you run your regressions, especially time series data, you need to check whether the variables, both X variables and Y variables, are stationary or not. So this is the test, augmented Dickey-Fuller test. Do this test first, okay? So let's do it. So if I want to see Y, okay, I open it. then view. Okay, did you see that? Unit root test. Did you see that? Unit root test. Okay, test the type, augmented Dickey-Fuller. Did you see that? Augmented Dickey-Fuller. Then test for unit root. Level. Level means the original y. Okay, so I'm choosing level. Okay, included in test equation. So look at the three words. One is intercept. The other one is trend and intercept. Do you see that? Intercept and trend and intercept. So you can try just intercept only. So which is 28, and trend with intercept is 29. 28 and 29. Okay, none means 27. Okay, you can see, check either one of them. Okay, so let's do it. And look at this automatic selection. This parts, okay, there's a archaic, Schwartz, and a queen. Usually we use this either archaic or Schwartz. You can choose either one of them. Okay, never really doesn't make big difference, I think. Okay, so if we choose the Schwartz, then what's the maximum you have to choose? You know, this is just try and error. Okay, so why don't we just choose, you know, since, what kind of data is this? Let's see the data. That's annual data, right? This is annual data. Usually, if this is annual data, we will use, what do we use? Usually, if it is like seasonal data, since we have 4 seasons, so I'll choose 4. Since this annual data, you know, maybe 1 or 2, or less than 4, it'll be okay. Okay, so just try it. Okay, maybe I just put it 4. Okay, then I can hit, and this is augmented Dickey-Fuller. Okay, look at all this one. Before we do that, the first one is Dickey-Fuller test, and the rest of them, there's some other options. Okay, then let's just use augmented Dickey-Fuller test first. Okay. Okay, look at this output. Look at this output. This is the constant term. I just choose the constant term. Intercept only, right? I choose the intercept only. I do it. Well, let's do it one by one. Okay, this is 28. Okay, this is the usual. This is the usual test. T-test. Okay, look at this. This is what we call the beta, right? And the T statistic say what? This is exactly the same as, okay, this one. Okay? And the Dickey-Fuller augmented Dickey-Fuller test result is on the upper parts. Okay? And if it is 1% level, means alpha, 1%, 5%, 10%, this is what we call the critical value. And this critical value is different from the original t-test. Okay, it's different. Okay, so we have to base on this one. Okay, look at this one. The t statistic is 0.56, and the probability is 98. 0.98, what does that mean? Do we reject null hypothesis? Huh? Yes. Yes or no? Do not reject null hypothesis, right? Look at the p-value here, it's so high. Do not reject null hypothesis. So what does that mean? Non-stationary. Okay? Okay? Then if I use, so now do it again, okay? Unit root test. If I do trend and intercept, okay? I change it trend and intercept, that's 29. That's the result. This is the result. The probability, the t statistic is negative 2a something, and the critical is over there, and it's all bigger than those critical values, so means falls on the non-rejection region. And look at the probability, p is 0.20 something, so it's pretty high. Still non-stationary, right? Okay, and let me, since this is the 29 version, right? So it's more strict than 28. Okay, so if I go back to none, means I don't have intercept, I don't have t. Okay, let's see that. None. Okay. Look at this probability. It's 1. It's very, very big. Okay, because the condition is more loose. Okay, so 29 is controlled with the t and also the intercept. Therefore, the probability, yes. Oh, it can be negative, means poor. It can be negative, R square. It can be negative. Usually adjusted R square can be negative, and this R square cannot be negative. But here, I think this is time series data. It's really different from cross-sectional data. There's no, usually the time series data, unless you are doing forecasting. Otherwise, R squared means nothing. They're always high. For times compare with cross-sectional data, time series the R squared with time series data is always high because usually the time series data, related together, and that's what we call spurious because they have some variables which in terms of the time. So it's really spurious. So do not believe the R square of the time series data unless it's for forecasting. Because forecasting, we really wanted to have forecast something which is close to the original y values. Okay? All right, so look at this one. If you do the regular OLS test, this is significant. But this one, if the Dickey-Fuller test, it really is non-stationary. Okay? How about working with, I'm just doing Y, right? How about the rest of 3? PC, PB, and YD. You can sort of practice. So, do you have the same result with my e-views using the augmented Fuller test? So let me check with. Okay, we have PCP, PCPB, and the YD, right? So, Jose work with the PB and work with the PC, and either one of you who wanted to do YD individual and tell us the result you have. You want to do that, Steve? Oh. Actually, this is the exercise, our chapter, exercise number 6. And I think this is too easy for you. So I don't want to make this an assignments. I want to make another assignments more challenging to all of you. And that's, I haven't made it yet. Okay, let me do it. Then maybe due the following 2 weeks. Okay? I try to make it as soon as possible. And due on, today is May 4th, right? Then maybe it's May 18th, 2 weeks from today, right? So this will be the 4th assignments. When is the last week of the semester? June what? Wow, the time is consuming, right? It's almost. So if the next assignment is number 4, then number 5 will be the following 2 weeks. So it's +1. Also, it's the early June, right? Huh? Wow. So we don't have time. We run out of time. So maybe just only 5 assignments for this semester only. Okay, so we will have 2 more. Okay, one will due 18th, the other one due the early of June, right? Is what? The first week of the June before the final exam. June 8th. Well, no. I mean, maybe June 1st. June 1st, right? June 1st. So this is our basically scheduled. One due May 18th, the other one is June 1st. And we run out of time. We don't have time. I wanted to talk about Garch and Arch and also the forecasting. I don't do any forecasting yet. Well, next semester, well, they are all graduate. So this lady graduate. Well, well, this is next semester for me will be the first semester of the new academic year. So I'm teaching research methods, which is the easier part of this one. Okay, so do not come and attend that class. You don't have to. You don't have to. And time series data is just only this course. Only this course. So if you continue the next year, this time. But I need to, also teaching pretty similar to this. Well, I don't have another course in the IBM. Does any other teachers talk about time series in English? I mean, especially in English, right? Not in English, maybe in Chinese, but not in English. All right? That's the problem. That's why you take this course, because this is the only one course speaking in English. And I hope you understand my English. Okay, so you want to talk about which? Oh, really? Oh, what course? International finance. Okay. All right. Granger causality, you mean? Okay. Oh, Granger causality? Wow, good. VAR. Yeah, that's related to to this topic. Yeah, this course is more time series oriented. Well, maybe I'll design next semester, not next man, next year's next semester for time series is all in time series. I will kick out the chapter 8 and chapter 10. That's for cross-sectional data. If I kick out these two topic, maybe all in time series, then we can cover more. We can have plenty of time. But especially, this course is only 2 credit hours. I think that's the reason. We are run out of time because of the credit hours. Usually, maybe 3 credit hours is enough. Okay, but only 2 credit hours is a little bit, less time. Okay, say something about what you do the augmented Digger-Fuller test. This business students first. Just say, so what did you do? Is YD? Excuse me, Rachel. Is Rachel want to do the, you want to do Steve or Rachel? Who wanted to do? Okay, according to, okay. So you're working with YD variable, okay? So let me also show the result, okay? Then which version to use? You can choose either one of them. You don't have to do the 3 of them, but I think it's pretty similar. Trend and intercept, okay? Let's do trend and intercept. Then, well, just use 1. You mean use 1? Huh? Did you use 1? 4. My example just use 4. Maybe we try 2. Okay, let's try 2, okay. All right? Okay, what did you see? Not significant. Means non-stationary. Huh? Yeah, of course, the p-value is even higher, right? Yeah, of course. It's even higher. So usually we'll do this version. Yeah. Okay. So even we do this more rigid version, then the probability is still high, right? So if I change my legs, okay, let me just play a little bit, okay? If I change it to maybe 12, okay? See anything different? Look at this one. Look at this one. If I change my leg into 12, that is significant. Did you see that? So the legs matters for the stationarity or non-stationarity. But the leg, usually just try and error. And if we have some theory to follow, then you can use that leg. But since this one, I don't have it. Let me try that. I'm using 12, so it's significant, right? So if I use uh, if I use 6, excuse me, 6, it's not significant. If I'm using 8, it is, oh, if I'm using 8, it's still not significant. Did you see that? If I use lag, is even 8 is not significant. Okay? But if I use 12, then how about 10? You know, it doesn't make sense to you. The 10, look at 10, it's not significant, but 12 become very significant. Is any stories about this one? Well, this 12 is really significant. Let's make it, but for the previous, I don't know, you know, I have 12, I don't know. Well, actually, for this, since this is annual data, usually we don't do that many legs. You know, it doesn't make sense. So I'm just playing with that. But we know that before 12 is not significant. So I would rather conclude it is not stationary. I would rather conclude it is not non-stationary for the variable. Well, this is for lag 12. Less than lag 12 is not significant. I try up to 10. It's not significant.
So in as a whole, the variable YD is not significant.
Yeah, I would rather say it is not significant. You know, it really doesn't make sense that I'm going to use the lag of 12. Right? Okay. Okay. So this is the YD, right? Let's see what else. What? Then PB. So if you also use this one, and okay, look at this one. This is lag 6. Let me use a little bit smaller, maybe like 4 or 2. Let me see, use 2. Look at, if I use 4 or 6, that didn't change the probability. Okay? Who did PB? Who did PB? Yeah. What is your only constant, okay? Then, let me see. If you are using only constant, so let me try it. Unit rule test, only constant, so it's intercept. Then, what's the lag you are using? 6, okay. It's not significant. So it's non-stationary. Okay? Non-stationary. Okay, then PC. Okay, let's see. The PC. View. So which word do you use? Just intercept? Okay. Why don't you want to use T? Any reasons to just trying? Oh, you have done all of them? Let me see. Oh, okay. Oh, what's quadratic? So what's the reason?
It will be different. Hebrews and Python will have different
Huh?
So also you didn't see so you don't know what you use.
What do you mean by that? So what do you mean? So PC, then which version do you use? Intercept only, then lag 4, okay? It's not significant, right? Is this the answer is yours? Exactly the same, okay. I mean, critical value is different. In Python, it's different. Might be different. I don't know why. I don't know why. Oh, same critical value? Good. Good. P-value is different in Python. But actually is is still big, still not significant. So it's fine. Okay? All right, so it looks like all the y variable and x variables are not significant. Okay? But then we are out of story since they are not significant. So the regression we run it before is all wrong. Well, in this situation, if you see that variables are non-stationary, there's one concept called co-integrate. Well, the co-integrate will have another way to check. All of them together, maybe they co-integrate. Therefore, they still can run the regression. No, it's different. The augmented Dickey-Fuller test is to test the individual variables is stationary or non-stationary. Well, co-integrate is another test to see that if I put all this non-stationary variable together as a regression equation, whether it will become a stationary or not. So we'll talk about that next week. Okay? All right? So what we learned today is okay for all of you? You understand it? Okay. All right. So see you next week.